to go, Phil? Good to go. Excellent. Okay, welcome. It gives me great pleasure to welcome you all on campus to the AI Quorum NLP workshop. My name's Tim Baldwin. I'm a professor at the university and the head of the NLP department. I'll do more of an intro of the department and me very briefly as part of my opening remarks. I promise I don't have too many slides. So I just wanted to give you a bit of an overview of the workshop itself and sneak in a little bit of an advertorial for the NLP department and MBZUAI, just because we are hosts and we're very new. So the AI Quorum series, what it's all about, it was kicked off in the last couple of months. I will read off the slide. So it's a series of gatherings designed to stimulate cutting-edge AI research with leading scientists and share an understanding of the discipline as a force for good. The series is strategic and high-level by design. It's focused on curiosity, collaboration, authenticity, and the pursuit of excellence. So in that spirit, we are going to have the AI version of it today. It's a mix of workshops, and we had a strategic retreat about a month or so ago. The other workshops have taken quite a different approach to it, much more sort of focus on a particular topic, particularly interdisciplinary topics on things like collaborative learning or low dimensionality and deep neural networks, sort of very specific technical topics. We're doing something much broader, doing something a little bit different for the first of the NLP workshops that I'll say more about in a moment. So the theme for today is NLP, as in natural language processing, in case there's any doubt. Where are we at? Where should we be? And how do we get there? Now, the way that the workshop is structured is we have 8 truly extraordinary speakers on campus, well, 7 on campus, 1 online. I very deliberately gave them very few instructions. I said, interpret as you will, ad lib as you will, be as controversial as you want, push back on any underlying premises in this statement as much as you want. But you know, I guess anyone who knows anything about NLP, modern day NLP, even if you'd only woken up 3 days ago, perhaps, and discovered NLP and were on Twitter, you would have seen all of the flurry of posts about ChatGPT that have been coming out as sort of the latest generation of, as in, you know, the earlier generation would have been all of 2 weeks ago with Galactica, but yeah, that's kind of the era that we live in. So yet another generative large language model with all sorts of crazy capabilities and shortcomings in various ways. So yeah, that's sort of very much where NLP is at, but I don't want to bias anything in terms of that's going to be the focus of today. As I say, people I hope have interpreted this in very different ways, which will lead to a very diverse series of presentations culminating in a panel at the end. So I also didn't do a lot of advertising of the workshop, I have to confess. I don't think the actual schedule for or program for the workshop was advertised formally. So let me do the reveal for our stealth workshop. Well done for finding it. So other than me doing the opening, as I say, it's a series of presentations from our individual speakers. Rather than introducing them on the way, I thought I'd do a batch intro. And one version of the batch intro would simply be to say, you know, these are leading lights, sort of either sort of very much the new generation or sort of people who've been in the field for decades and have built the foundation stones on which the field is built, would be a sweeping statement. But let me go through and introduce them individually, just to give you a little bit more context than that, because yeah, they all deserve recognition for their incredible achievements. So first presenter will be Claire Cardiff from Cornell. Claire, and forgive me for looking at my notes at this point, is the John C. Ford Professor of Engineering in Computer Science at Cornell. She was the founding chair of the Information Science Department. As with all of our speakers, she's done incredible things, and in acknowledgement of that, she's a fellow of ACL, ACM, and the American Association for the Advancement of Science. As I say, I could spend the next 5 minutes introducing Claire, but that might defeat the purpose of the workshop. Next up is Mark Steedman from Edinburgh. Mark's Chair of Computer Science in the School of Informatics at the University of Edinburgh. He also has a big long list of fellowships, including ACL, British Academy, Royal Society of Edinburgh, MBZUAI. And I think my favourite nugget of information, which says it all about the evergreen Mark, is in consecutive years, he was first the keynote speaker at ACL, as in kind of in recognition that he was a guy who was leading the field. And then the very next year, he was the Lifetime Achievement Awardee at ACL. So he is both leading the field as well as sort of has a lifetime of achievement that was recognized. I don't think we'll ever have that repeated in time. We're going to have a break for about half an hour, just out in the courtyard here. Then we'll be back with Barbara Plunk. Barbara recently moved to LMU in Munich. So she's the chair for AI and computational linguistics at LMU Munich, as well as being a professor at the IT University of Copenhagen. And again, she has many, many awards to her name. Really needs no introduction. Yejin is next from the University of Washington and AI2. Yejin is the Brett Helsel Professor of Computer Science at UW, in addition to being a Senior Research Manager at the Allen AI Institute for Artificial Intelligence. The Allen Institute for Artificial Intelligence, AI2. If you look at just the last 2 years of Yejin even, I think she's got Best Paper Awards at ICML, NeurIPS, NACL and AAAI, and she happens to be a MacArthur fellow, because why not? So that's Yejin. We'll then have lunch, come back then with Ed Hovey. So Ed's professor and executive director of Melbourne Connect at the University of Melbourne and a research professor at CMU. Also, too many achievements to list, including being an ACL and AAAI fellow. Irina is next, Irina Gurovic. She's a professor at the Department of Computer Science. There'll be a test on this at the end, of course, at TU Darmstadt, where she directs the Ubiquitous Knowledge Processing Lab. She's an ACL fellow. She's vice president of the ACL. And again, many, many achievements to her name. We then have DE from Stanford. So she recently moved from Georgia Tech to Stanford, where she's an assistant professor. She was Samsung AI Researcher of the Year in 2021 and has, again, many awards, including at ACL and CSCW very recently. And then, as our lone online person, we have Mohit Bansal, from UNC, University of North Carolina, Chapel Hill, who's the John R. and Louise S. Parker Professor there and directs the Merge Lab. And again, sort of has a big long list of best paper awards at places like ACL, CVPR, EACL, Colling and Connell. So it should be a good day, suffice to say, given the caliber of our speakers. So we'll then finish up, if that wasn't enough, with a panel. And anyone who's ever organized a workshop will tell you, if you're going to have a panel, never have more than 4 speakers. What we're going to do is have guests, because why not? So we're going to have our 7 in-person speakers, plus our very own Preslav Nakov, all coming up to the front. What I want to do is, after having given everyone the opportunity to sort of present their own thoughts and ideas and perspectives on the topic, to then sort of come back and have a little bit of maybe crossfire, maybe a little bit of cross-fertilization of those ideas. I don't expect that we'll actually end up with any consensus, but at least reflect perhaps and open the floor to questions as part of that. So we'll see how we go with that one at the end. And we'll see how we go. We aim to finish up by 5:30. We may still be here at 8:30, given all the things there are to say, but let's not aim for that. So let me just spend a couple of minutes. I don't want to eat into the time of our speakers, just talking for 2 minutes about the university and the department of NLP here, given that we are very new. So the university, rather than kind of giving you a spiel about university, I thought I would present it in numbers, because we're NLP people, we know that the best way to evaluate anything is with way too many numbers, right? So here's my numeric evaluation of MBZUAI. We are 2 years old. We have almost 3, so we're almost out of the terrible toddler stage. 40 faculty and growing. The aim is to double that by the end of next year. About 100 researchers and growing. 3 departments, so we're basically a single faculty university at the moment in computer vision, machine learning, NLP. Yeah. Whether you believe in rankings or not, it's only one dimension of any institution, of course, but a little bit of a stat that I pulled out was, according to CS rankings, at least, we're one of only 11 institutions in the world to be top 40 across all of those fields. Cornell, Stanford, CMU are also in that group of universities, for example, represented today. We're a graduate-only university, so we have 250 students, masters and PhD. We're about 31% female at the moment. A very rich mix of nationalities amongst our students, so well over 40 nationalities amongst our students. We are 100% green powered. Perhaps given the climate, that's an easier claim to live up to. So you may have seen a big solar farm as you came in. So that's where our power comes from on campus. And I mean, another sort of perhaps surprising tidbit, given people's knowledge about the region, is mix of some of our international collaborations that we've put together over the last 18 months or so. So in particular, the Weizmann Institute of Science in Israel, through the Abraham Accord. NLP department, very briefly. So we're a department of 4.45. We're very precise with our numbers, as in we have 4 full-time and 2 part-time faculty at the moment, with more in the pipeline. You'll see my face up there as chair, Preslav, who you'll see later is deputy chair of the department. And we have Mohammed Abdul Magid, who has his hand raised, and Hanan Aldamaki, who is just smiling at me. You can meet later in the second row there, third row. And then Bikshar Raj is fractional with us at the moment. He'll join us full-time from January 1st from CMU as a speech professor. And Shadi Shahata is also not here at the moment, but another fractional appointment at the moment. In the pipeline, and some of them I'm delighted to say are here. We have Alham Aji, who's joining us from Amazon, and prior to that, he was in Edinburgh. So this is sort of somewhat in chronological order. So this is in January, Alham will join, Tamar will join us part-time and then go full-time later from the University of Houston. Ted Briscoe will join us in February from Cambridge, Chakochma from Bath. Teresa Lin, as the head of NLP research engagement, will join us from Dublin City University. Nizar is not here at the moment, is rushing around doing lots of NLP things, so he's going to be an adjunct faculty with us, as will Irina, who's one of our speakers today. So very excited about that. And as I say, so watch this space. We're very much actively hiring, so if you want your face up there, come and chat. So with that, I've probably taken up too much time. Let the games commence. Claire. Yes, I'll just find some cards.
Okay. Just wave.
Yeah. Wave the minutes or even 5 minutes. So you keep us thinking as 30 to 35 minutes, and then we'll have 5 to 10 minutes for questions, but then on the next speaker.
It'll be okay. We're ready, right? 25.
It's not going there. It's not going there. The output is not going there. The output is not going to online. Oh.
So it's bear with us, we're multicasting to Zoom and YouTube and various things, and
Meeting
it's not all linking up.
Okay. Okay. Meeting.
We've got enough.
Meeting ID. Hey, it's not going soon. Meeting ID. Yeah, invite top right now. Invite. Yeah. 98978. 978-388-37410, right? కొంచెం పొరం again. Passport.
I can also.
This time reading out your life story
I can also copy it and put it, so.
Can you make me the panelist? Can you make me the panelist? Attendees, go attendees, and Clark, make me the panelist. Clark.
Okay, she's on Zoom.
Yeah.
Yeah, she can share her screen.
Yeah.
Yep. Okay, let's share the screen. Presentation. This is your presentation, no?
Yes.
But we have to share the presentation.
You can get it.
Would you be able to, when it's, microphone? Just give you the previous talk about.
You can get it in Zoom, right? No,
We're
you
good,
can
we're
get the
starting?
feed from Zoom.
Okay.
These things,
Yes.
now you get it, right?
We had this.
You can share it from the Zoom link, not the paper output.
Is it good?
You can do that from the back. But no, high. Okay, without further ado.
Okay, so we're all mic'd up here. There's feedback here, so let me see. I'll turn off the sound. Okay, that's better. So first, thanks to Tim and everybody here for getting us all together, and for my very first ride in a golf cart this morning. It was very exciting. And following Tim's lead in terms of not providing much in the way of advice on what to cover, he also said we didn't have to have a title. So it's my first time giving a talk without a title. Okay, so the topic, where are we now in NLP versus where should we be? And then second, if I have any ideas on how do we get there. So let me start. So where we are now, and Tim alluded to this, so maybe others will have similar initial slides. We're in the era of large language models. They've transformed the field, and that's no pun intended. They've been trained on vast amounts of text and have seemingly acquired linguistic capabilities. This is both for natural language interpretation as well as natural language generation, and are able to encode world knowledge of various forms. In addition, the large language models are for the most part general purpose, and to my mind, that's a good thing. So recently, and I think in the next upcoming years, it seems that a lot of NLP work is focused on first understanding exactly what is learned in these models via probing, prompting, and then a series of black box workshops is a good place to look for info on that. How exactly to adapt the large language models for specific NLP applications. And this includes changes to the neural network modeling and also manipulation of training data and training schemes. It's not able to see the screen. Okay. So we've been trying to understand what exactly is learned in the models, how do we adapt them for specific NLP applications, and in particular, how to add what's missing. And this is mostly in the form of knowledge, maybe domain-specific knowledge, task-specific knowledge, and reasoning skills, for example, common sense reasoning. So where should we be and how do we get there? So I think that, that depends. Are you interested in building NLP applications that really work for end users, really practical stuff? Or are you interested in building true artificial intelligence systems that operate in the world as well as or better than people? Okay, so it may be disappointing, but I am mostly interested in the former. But I came from the bigger background. And so I'm also interested in the latter. And at the end, if you have questions on my opinions on that, you can ask. But for now, for the rest of the talk, I'm going to be focusing on the more practical natural language applications and what's involved in that. And it's through my particular lens, which is one of information extraction. And I can see Ed Hovey holding his head. So I'm not sure that's good. But so the goal in information extraction is to get computers to read text for us, extract and organize the relevant information it contains according to our needs. And so this audience already knows this. So where should we be in terms of NLP today? So I thought, and this has been bugging me, minimally, we should be able to handle this old template filling task, essentially complex event extraction that was set out for the field in the early to mid 1990s. We should be able to do that. What's the task? This is from the 1991 evaluation of information extraction systems. The domain of interest for these systems was terrorist event extraction. So we have terrorist events from Latin America. What kinds of information were supposed to be extracted? Well, there were 18 different slots, roles, arguments, fields, things like the type of the incident, the date and location, who were the perpetrators, what terrorist organization were they from, what were the physical targets and human targets of the attack, and what were the effects of the attack. So a real example, this is an input text from those days, all caps, annoyingly. This was from 1990 from Bogota, and it's discussing Senator Velez, who's described and referred to in various ways throughout the text. And it's about his kidnapping, which is also mentioned in different ways throughout the text. We know when it happened, basically. Let's see here, and where it happened. The perpetrators were, the kidnappers were 3 heavily armed men, and they're referred to later as well. So what actually just, okay, as the they. The extraditables is the group that they're from. And so the output should look something like the following. So all of those under bracketed items were things that were supposed to get extracted and potentially classified. But in the output, you'll see the 18 slots. A bunch of them are really strings that were supposed to be extracted and descriptions of the entities were extracted. Other fields are classification based, so they're taken from a fixed set of possible categories. Still other fields were numeric or required some kind of normalization, so location and time. Okay, so we should do this. We should be able to do this. And we should be able to do it better than the early systems. So this is the top systems in this evaluation. They're getting about, precision is on the y-axis, recall is on the x-axis. Top systems are getting about 40 to 50% recall, 55 to 65% precision. One thing to note is that building these systems really did take a long time. So greater and sometimes much greater than 1 person year of effort to build a single extraction system in a single domain. Okay, classification-based fields were easier. So that's slightly higher than the overall scores. And the extraction-based fields were the ones that were harder. So this is the original overall scores. If you look at 3 of the string fills, you'll see that the numbers are a bit lower. Okay, so these were harder. So we hope maybe we're doing better on these. And that's the score. So in general, the recall is much lower than across all of the slots. And the precision is sometimes higher for physical targets, but otherwise it's a bit lower. Okay, so there was a lot of room for improvement in that time. Can today's systems do better? So remember, there really are a lot of complex phenomena going on here. In theory, at least, the systems need a lot of linguistic capabilities or subsystems like parsing, semantic role filling, semantic tagging, lexicons of different sorts. And the task is really document level extraction of entities, and those are slot fillers, and of complex events where there's one template for each relevant event in the text. And so this in particular means we needed to do co-reference resolution. You have to do co-reference resolution for this task. And it's hard also because relevant information can be spread across the document. And also information mentioned once might be shared across different templates. So this was really, it's really hard. And again, huge person hour time commitment to develop. So if you look at recent work on event extraction, this is quite recent. These systems handle entity and event extraction using neural network techniques. They do not involve NLP subcomponents, no feature engineering, and much faster development. And they're getting better or comparable performance to earlier machine learning based approaches to the task. The downside, of course, is that more training data is much, much better, and sometimes that's not available. But this work in particular isn't actually handling the task that was set out earlier. In particular, these systems are looking at extracting events within a single sentence. So you have to have an event trigger in the sentence, and then any of the slots that happen to any arguments of the event that appear within that sentence are to be extracted. But that's not document level information extraction. It's not even close. So is the real work now on, I mean, this is already pretty recent. So is there work on document level information extraction? And there is, and it's all fairly new. So work out of UW, Wadden et al. Try to treat this task as finding all possible spans in the text, and then finding relations among the spans and classifying those relations. Work from my group, we tried to treat the task as question answering, where each slot fill was is a question, and we use systems to try to find the answers. I should point out that all of this is only going to deal with the string fills, so the harder things to extract. Paolini et al. Did not design the system specifically for information extraction. They have a general purpose text-to-text system. And so effectively, we looked at that and use it to treat information extraction as a machine translation task. The input is a document, and then the output is that document as if it's annotated with HTML to indicate the templates and the slot fillers. These systems, again, were not really designed for document level template extraction, but they can be coerced to do that. Some newer work does this. This is a work from one of my students, Shinya Du, and also with great help from Sasha Rush. We looked at it in terms of a natural language generation task. And I'll tell you quickly how that works just at a high level. And then Hung Lee, is Hung here? No. Okay. A lot of good work is coming out of Hung's group. In particular, is this new work in the end I really like, and I'll maybe get a chance to explain why. So there is work, but how do we know whether it's it's working like better or worse than the original systems. So let me give you a quick overview of actually what's the time here, because I can skip the overview of the system because that doesn't really. That's a lot. Okay, all right, so I'll give a quick overview of this, of the information extraction as natural language generation, and then we'll show you what happens if we do a head-to-head comparison with earlier systems. Okay, so what we're doing here, BERT is the center of this system. The input will be a document, and then the output is essentially a linearization of the desired events extracted. Initially assume there's just going to be one event in a document, but there'll actually be more. And I'll show how this is actually made to work. So we have BERT. BERT for us is a little bit odd, but we're using it a single BERT system as both the encoder and decoder, and they'll get trained together. So in terms of method, this is an interesting piece. Input for training and for test is the document. I'm sorry, these brackets should not be there. In the output, the idea is that we will have a fixed ordering on all of the roles associated with a particular event type. I'm sorry, a particular set of events. So there's a fixed ordering of the roles. And then the system has to first produce all of the slot fillers for the first role, followed by a separator, then all of the slot fillers associated with the second role, and so on. We don't extract the whole string. The system will just identify the index of the first word in the extracted string and the last word in the extracted string. But it's a format that then you can recreate the output templates directly and very easily. We didn't actually think this would work, but it works okay. Input will be the whole text. The output is done auto-regressively. We'll first output the first roles entities. And here it was 2 men. So this is the perpetrators are first. Their organization second. Each time we take what we've just output and use that to start the next, and it continues like this for generation. Okay. As I mentioned, the encoder decoder in a single model is a little new, but a masking strategy enables this generative learning property with a single transformer and no additional parameterization. All right, it does extend to multiple templates. And the only thing that's different is that we'll first, we assume that we're looking for all different, a fixed set of types of events. And the system is trained to produce all of, say, the attacks first, in the way I just described, one after another, and then all of the bombings, and then all the way through the possible event types. And this is called GTT, and so you'll see this in the results. All right, so we looked at the MUC4 data set. This is based on the MUC3 data set that you saw results for before. It has 1,300 documents for training, 200 for development, 200 for test set. And we'll show a comparison to the top performing MUC4 systems from 1992, along with not just our system, but a couple of the others that I mentioned earlier. How do we do this? So there's new work that we have on automating error analysis for document level event extraction. And what we're trying to do is make it easy for people to compare systems. So you can take a look at that if you want. Here's the results. So at the top, you'll see 4 systems that were among the top from MUC4. The GE system is by far the best there. And these are the new systems. Ours is the GTT, DIG++ is the span-based architecture. And then TANL is this approach that treats information extraction as machine translation. So input document gets translated into an HTML version of it with the HTML that actually indicates the templates and the structure. And what do we see? We're not as good as the best system back then. That's a little disappointing. The best of the early models performs better than any of the new models. It does a better job balancing precision and recall. The neural network models exhibit much higher precision and much lower recall, which is not what I had expected. In the recent work, we would see that the neural network models were better at recall, but that's not the case for here. Part of the new work is looking more closely at the different types of errors that systems can make. And so in here, you'll see the early, well, let me just do this. Okay, the black line is showing all of the older systems. The new systems are at the top, and then we just got these new results like last week. This is the machine translation-based system, and so it's at the bottom. What do we see? So span errors, whoops, let me go back. I can't go back. The early models have more span errors. So span errors are these orange, the orange blocks. So they're not finding spans as good as well as the new systems. The early models have fewer missing templates and fewer missing role fillers. Those are the dark green and the light green at the far end. At the same time, they also have more spurious templates and spurious role fillers, and those are the pink items in the middle. And they have fewer incorrect role errors, but there's hardly any incorrect role errors. They're in these little blue areas. So both systems are finding correct role fillers well. The main source of error for both the early and the new systems is low recall because of missing templates and missing role fillers. Okay, so how do we get there? So this is a little disappointing. So one of the things that's really nice though is that the new systems are easier to train and to build. It's not a person-year effort. We can train up quite quickly given some training data. But how do we get there? I think that we have to focus on discourse level natural language understanding tasks a lot more than has been done so far, and solve the relevant neural network modeling and representation issues. So this is not just for document level event extraction, but there's a lot of tasks that are having the same problems, document level information extraction in general, not just events. Anything at the corpus level, so things for knowledge-based population, for example, have to understand things at the document level before they can handle them at the corpus level. Question answering tasks that require reasoning, argument interpretation and generation. Dialogue understanding falls into this category as well. Narrative interpretation, so interpreting novels, summarizing novels, long document summarization. All of these are systems, are tasks where discourse level representation is key. And there hasn't been enough work in that so far. So what are the document level representations that we need in order to handle these tasks better? And how can we get the neural network modeling systems to encode that and to incorporate some of the discourse constraints that help us to help people to perform these tasks. How do we get there? I don't know, but I like always looking at relevant research from other fields to see how they handle, in particular, these modeling decisions. So cognitive science, psychology and social psychology, linguistics, in particular, work on theories of pragmatics and sociology. So that is the end. There's no end slide either. But thanks for
First of all, thank you very much. So there are some interconnections to my talk later during the day. So there's a growing body of research on long document transformers of all kinds. So don't they provide some relevant input to this? And if not, what are the main bottlenecks from your point of view?
Yeah, so we've looked at some of the long document systems. So the systems that will handle more than 512 tokens. And they're really designed to make it possible to just have a longer document, but they're not doing anything specific in terms of representation, nothing. And so there's the higher level representations that we need to, for example, do co-reference well or recognize multiple events and their connections. It's not there.
So what about pre-training on relevant tasks or injecting some sort of discourse structure?
So that's the kind of stuff that I think that we need to do much better.
Thank you.
Thanks.
So following on from that question, there's sort of two responses one could imagine, right? One is you need more training data because I imagine you just had a few thousand documents. And the other one is exactly what you said, having deeper representations and starting to go deeper than just the surface level and starting to tie things together at some semantic, whatever that means, level, right? That's where also my talk is going to go. Seems to be like the right thing to do. These machines work at the surface level almost exclusively. They do a tiny bit of generalization.
Yeah.
We shouldn't expect that they do any better than just that.
Yeah, no, I think that's right. The fact that they do is kind of amazing. So we did look at a couple of other, there aren't that many good document level information extraction data sets. So we looked at two others, one of which has less training data than the mock system, the mock task, and one that has much more. And the results are quite similar for the new systems. Now we can't compare the old systems on the new data sets because they don't exist. But we're seeing this similar trend even when we have more training data.
Have we lost anything in this move from human-based or like systems that took a lot of human time to create to these transform-based systems? Or what have we lost?
What have we lost? So, I mean, I guess if you saw that there was just this one system that was really, really good. The rest were quite a bit below that. There's a lot of engineering that can be done if you really know the domain and you've worked on it for many years, like that group. And so if you have enough time, I think you can probably make just maybe not neural network systems, but machine learning based systems do much better than the older systems, but it would take effort.
So I'm puzzled by your observation that transformers give you high precision and lower recall, and I'm wondering whether this can be due to the difference in the time when kind of the timing between the documents that we are looking into, because typically for information extraction, you have these old documents from 20 years ago or something, and those are completely different events. And the transformer models are trained on much more contemporary language. I'm just wondering kind of what are your thoughts on this diachronic shift between the two?
So that's a good point. It could be a function of the mismatch in training data, although I suspect there's a lot of old text that was also used to train BERT, for example. And another problem that could explain some, but not all, is that that particular data set, the MUC data set, I think that there isn't consistent span annotations. So I think there are things that we might consider to be errors in the data, both testing data and training data, and that's causing causing some problems, although that would also affect precision. So no answers.
So Claire, thanks for the talk. You mentioned co-reference as a key task in the subtask of the MUC task, and that seems to be a case where the technique of looking at the whole document is bound to break down in long document situations. And as you say, the new long document techniques don't seem to really address it. And one of the ideas that was very strong in the early days of co-reference was incrementality, that we're actually sort of changing our model as we go through the document. Do you think there's a place for that kind of model? And do you see a way to bring that back into the neural models that we're looking at the moment?
Yeah, so I think that's a great idea. I guess there are some pieces of that are out there already. So explicitly having a memory on the side that can be updated incrementally as the text is processed could be one way to get around that. And I think that would be a good thing to look at. Excellent point.
Perhaps let me sneak in one question while we're setting up Mark's slides. I don't know if you agree with this characterization of kind of the reflections on MUC, but my interpretation is, you had some very different tasks from year to year, and each year they kind of had to start over, and sort of after however many iterations it was of that, 8 or 9, I can't remember the number.
A few.
Yeah. The sort of feeling was, well, hang on, what have we learned in terms of more general principles of IE? And the answer was, well, not a lot, because we had to sort of do over each time. I wonder, in terms of sort of transfer from these sort of very different verticals in terms of specific MUC IE tasks from one year to the next, with the more recent models, whether it's sort of simple multitask learning or something more sophisticated than that. But is there at least a potential for that sort of carryover from one year to the next, which wasn't possible, and realizing that they were very different information extraction tasks, but at least sensitizing our models, modern models, it's easier to sort of sensitize them to, well, what is a slot and what is a role,
right.
sort of more general principles, I guess, of
Right.
semantics. I mean, do you think there are any links to that idea?
I think that's an excellent. I never thought of that, so I'm happy I came to Abu Dhabi.
Wow.
But yeah, so multitask. So using multiple information extraction data sets as pre-training or some additional training, that I don't know what that will help exactly with, but it could help with exactly these discourse issues, at least a bit.
Yeah, it'd be interesting to see.
Yeah.
Wonderful. Okay, join me in thanking Claire again for a sparkling talk. So our next speaker is Mark Steedman from the University of Edinburgh, who's just getting wired up.
Am I on? Okay. So I've been thinking for some time about the problem that Tim raised in his questions. So, okay. Sorry. Okay, so here's the questions. So where are we? Well, we've made a lot of progress, but one of the things that I'm struck by talking to my students and trying to advance their projects with them is that we're in the era of very large language models, and there's a lot of magical thinking about what those models are doing. So my students tend to sort of think that they're doing everything, and that all you have to do with these models is show them a few examples of what you want them to do, and that will point them to the area of their memorization of text that will deal with the problem. And I find myself having to say to my students that I don't think that that's necessarily going to work, particularly for the problems that we're looking at. And I'm going to argue that where we should be is combining the things that we learned when we used to think in terms of logic-based or structurally based, symbolic-based methods, and we have to integrate those with language model-based methods. Language models are very good at telling you what unseen examples are most similar to in your training data, but I don't think that that's a substitute for structured models. And in particular, in question answering, I don't think it's a substitute for inference from one state to another. And so my talk is really going to be about inference in question answering. And the way I'm going to argue that we should get there is, first of all, getting away from logic as it's developed by logicians who really have very different questions in mind. Also, by making the logic scale to the kinds of problems that we're dealing with when we deal with question answering from text. And by exploiting the way that language models actually work. I don't think it's wise to think that language models must be inducing the kind of structures that we use to solve these tasks ourselves. I think there's every indication, and I'm going to briefly refer to some of our work kind of probing this question. I think there's every indication that language models, large language models, simply work in a quite different way from the way that we work. And we shouldn't waste our time trying to show that they have the same kind of internal structure as ourselves, because they're just doing it a different way. And the different way that they're doing it is immensely powerful and can be leveraged to do things that we can't do any other way. These models are here to stay, but I think that we must find out what they're actually doing and exploit their strengths, rather than thinking that they must be learning hidden syntax and semantics and even inference. And I'm going to argue that the inference is really the point of the large language model. So very briefly, looking around the audience, I wasn't quite sure who the audience were going to be. So I think the motivation is probably very obvious to the audience that is actually here. But I'll say it anyway. Most information that we need to answer questions that we can't answer just by thinking about them is out there somewhere on the web in the form of text or spoken natural language, rather than as structured data, as knowledge graphs like Freebase and the rest of it. Even in knowledge graphs and databases, there's very often a free text comment field for entering information that doesn't fit into the existing data structure. In other words, something that you've noticed that you couldn't get into the standard record structure. And very often that is the most interesting part of the database entry, because it points you to the way the database is going to change in future and the new things that it's going to have to represent. So we would like to get these natural language data into databases or knowledge graphs using natural language processing, because they're sitting there in free text. We would also like to interrogate and update these data structures in natural language. And that is a very difficult problem to solve, as the previous talk made quite clear, because the problem of open domain question answering is that there are always too many ways of asking and answering the same question. So it's very rarely the case that the form of words that the user chooses to ask the question is actually anything like the form of words that the answer is latent in the text that is being queried. So I'm going to start with a toy example, and it is a toy example because I'm going to use it as a running example to try and make the ideas that I'm going to present concrete. You want to know who played against Manchester United last night. And the text says that Arsenal beat Manchester United, or Manchester United's defeat by Arsenal is referred to. Arsenal obliterated Manchester United. It can say all sorts of things. So if you just naively build, you're sitting there looking at your news feed and you're building a knowledge graph with some kind of parser, some kind of low-level information extractor of the kind that was applied in the early days of Mark that we heard about in the previous lecture. If you just build a knowledge graph based on those relations found in the text, which when I was a graduate student, we called a semantic network, an object-centered graph, you won't be able to interrogate it effectively because of the mismatch, the impedance mismatch between question and answer. Conversely, if you build a knowledge graph using a graph query language relations, such as the ones that you find in Freebase, then querying it to with natural language, you can train an end-to-end model, but it will need to be robust to the same variation in natural language input. Now, for this toy example, of course, you would just Google the question and you would get back a set of snippets from which you could work out the answer to your question. All that stuff about Arsenal beating Manchester United would tell you that who Manchester United played. But that doesn't always work. So if one of the questions that I came across actually quite a while ago, but it still is the case that it fails, is what are Miles Davis recordings without Fender Rhodes piano? And if you do that, you get back a set of snippets. You can't read them, but these are the ones I got back. And they're all about records by Miles Davis with Fender Rhodes piano, which is what you don't want, or about Fender Rhodes piano, which you probably also don't want either. What is the problem here? Well, the problem arises from the lack of a usable natural language semantics, and all that work in symbolic frameworks a long time ago really didn't produce a usable natural language semantics. It's just too big a question, too big a problem for us to do common sense inference on the basis of. And there are two modern solutions to that problem. And I'm going to talk about them both in the remainder of the talk. One of them is to use a pre-trained language model as a sort of latent natural language inference data set, as a latent entailment graph, that it's seen so much text that it knows that being defeated by somebody if you're a sports team entails playing against them. The other solution is to try and induce something more old-fashioned, a structured entailment graph from text by machine reading, and to just read so much text that you work out that if two teams are in the defeat relation, then somewhere else in the text, you read about them playing against each other. If you read about somebody being elected president, then you also read about them running for president. So if the question is who ran for, when did Trump run for president, you can work that out from the fact that he was elected. So I'm going to talk about these two solutions to the problem in the remainder of the task. The basic encoder-decoder architecture in NLP that was deployed in the last talk we inherit this from machine translation. and it offers a very general method for sequence-to-sequence alignment. And this method, of course, can be used to learn semantic parsers as direct transducers from natural language meaning to meaning representations such as a graph query language. That has been a very successful approach. It only sort of works because this approach, which avoids the use of a grammar entirely, is very bad at generalization. So if it's presented with a sentence in which a relation that it's seen many times is presented in conjunction with some entities that it's seen many times, but it hasn't seen the relation and the entities in that combination, then it fails to generalize very spectacularly. And a major cottage industry at the moment that many of my colleagues at Edinburgh, and indeed I myself, are working on is the problem of compositional generalization. How can you get these models to know what to do with unseen combinations of seen elements? Of course, unseen combinations of seen elements is exactly what grammars were invented for. They are invented for compositional generalization. And in fact, my colleagues are trying to re-import notions that are very like grammar into these sequence-to-sequence models. They can also, of course, be used as a closed model for question answering by masking during training. And that's a sensationally effective way of answering questions, provided those questions have been asked before, and the answer is to be found in the large amounts of text that the large language model has been trained on. So these are examples of the kind of successes and some of the errors that are characteristic of these models. Can they be used for text inference? In other words, can they be used for bridging between the fact that the text talks about defeat and your question was about the event in the first place, the playing event that beat event entails? And Heinrich Schütze and his students have been working on this by methods like fine-tuning large language models on entailment data sets, and also probing with things that might be found in the text that suggest the entailment relations. I'm going to argue that this is not clearly an approach that is working so far. Heinrich has had some success on this, but it's the evaluation of supervised text inference, in other words, text inference done by fine-tuned large language models, is really an open problem. Natural language inference data sets, SNLI and XNLI and the rest of them, are riddled with artifacts that machine learning can learn as a proxy for the task that you're really interested in, which is entailment. This is partly because the data sets that they're trained on also fail to include the false inverses of directional entailment. Playing doesn't entail being defeated in a match, but being defeated in a match entails playing. And large language models, if you're not very careful, will treat those two questions as the same, and will give the same answer depending on the data. So I'm going to cut this short because I'm running out of time. Our probings of Heinrich's model and other models of text inference, supervised models of text inference, suggest that actually these are not learning anything directional at all, and that large language models are really working on the basis of memorizing the training data. If you've got a trillion parameters, and you know these days it's even more than a trillion parameters, you can memorize the training data. And they excel at tasks where the memorized text actually contains something similar to the question. And
for natural language inference, it's likely that the training text doesn't include explicit sequences like this happened, therefore that happened, or this happened because that happened, which is a sort of probe that might work for inference. So I'm going to talk in the remainder of the talk about an unsupervised method where we don't rely on having human annotated inference data sets to train on. So we're going to build a large unsupervised natural language entailment by parsing large amounts of multiply authored text about the same events. So at the moment, this has to be news text because there are lots of newspapers writing about the same events because the people are interested in the same things. And one newspaper article will say that Manchester United played Watford, and the other will say that they beat Watford or were beaten by Watford. So we learn from such observations that if we read about a statement about, if we look at the overlap between the pairs of entities that are involved in one type of event and the pairs of entities that are involved in another one, then we will be able to infer the entailment relation between those events if it exists. And I'm going to tell you briefly about some stuff that I've been doing over the last few years, where we've done this in English and in Chinese. And this is the work of, I should have said on my first slide that this is all the work of my students. And I'm going to mention them by name as we come to them. Javad Hosseini did the early work on building these entailment graphs. And this method, which I've described to you very briefly, and the details are in the paper, but essentially it involves reading large amounts of text for coincidences in statements about the same named entities. This method scales. So we practice on a corpus of news data, which is 20 million sentences. But when we really want to satisfy ourselves that the thing is working, we have a much larger data set. The 20 million data sets is the news spike corpus from Seattle. And we have our own corpus, which we are about to make available, which is an order of magnitude larger. But the problem with these things is that an order of magnitude larger data set for this method doesn't buy you that much. It buys you a just noticeable difference in coverage and accuracy, both. But it doesn't solve the problem of the Zipfian distribution of the relations that we're looking at. So the problem that this method faces is sparsity. It's high precision because if in an entailment rule, it probably is sound, but we have them with recall. So the thing that I'm going to talk about in the rest of the talk is whether we can smooth entailment graphs with non-directional language models. I'm going to assume that language models are essentially associative, and that what they are essentially learning is this multi-dimensional, very large dimensional sphere of similarity relations, where the radii of the sphere are dimensions of similarity. Maybe there's even a syntactic dimension of similarity in there somewhere. But it is similarity of association, similarity of text, the two things occur in, or the things occur in, the relations you're interested in occur in this large amount of text. So can we use this method that I'm assuming is essentially non-directional to smooth the directional entailment graphs? And can we do that without losing the directional precision of the precision of indirectional entailment? I'm going to skip over these two slides because I don't think they're that relevant to what I'm talking about. These are just statistics about this method. And really, the only thing to say about this is that these things are large, but they're not large enough. So we've done it for the news spike corpus of 20 million sentences, the news crawl sentence an order of magnitude bigger than that. And this is some statistics. There are some, you can think of it as a collection of type subgraphs. So there's a person-person type graph, a person-organization type graph. And there's some statistics at the bottom of the slide about the size of the entailment graphs that we are dealing with. And there's a few very large entailment graphs because of the weakness of the type system that we're using. The only thing, other thing I'll say is that this is a completely transferable method. If you have a named entity recognizer and a sound parser for your language and a corpus of news, you can just apply this technique out of the box. Well, I say that, but my student Teddy Lee did this. It took him about a year to do the first version of this thing there's a smaller and a larger Chinese news corpus. And these are the same statistics about it. It's actually a slightly stronger graph than the one that we built for English. And the reason it took him any time at all was that he had to do some actual intellectual work with the tools, because everything in Chinese is predicated on the assumption that Chinese is just like English and you can transfer all the stuff you did in English to Chinese, and that just isn't true. And in particular, the parser was no good and the named entity recognizer was no good. But apart from that, this is a transferable method. But it's sparse. So the rest of the talk is going to be about smoothing that graph. I'm actually running a little short of time. What's the weakness of this thing? Well, I'm going to talk about the premise and the hypothesis because that's the vocabulary that is used in the text entailment, the text inference data. But for our purposes of question answering, the hypothesis is the question and the premise is the thing that is actually in the text. So you've got a text, you made it into a knowledge graph offline, you know, in a few minutes offline in order to work with it. And there's a premise, you have a question and you have to say, is there a relation in the text that answers to this question, even if it's not an exact match for the question or hypothesis. Now, if the premise in the text and or the hypothesis, the question, is not in the entailment graph, then you're finished. All you can say is, I don't know, because the entailment graph has nothing to say. And that makes you think of soft methods, large methods, like large language models, and whether they can do anything to help. In particular, if we can find a premise prime, P prime, or a question prime, H prime, that actually are in the graph, then if the P prime that we found is the premise in the text, or the H prime that we found is entails the question in the text, it's actually asymmetric. Then if P prime entails H prime is in the graph, then by transitivity of entailment, the premise in the text does entail the answer to the question H. Otherwise, you should answer no, because you should believe that your method is complete. Or maybe you should answer, I don't know. The idea, and this is the work of my current student, Nick McKenna, is that what we should do is we should rely on the machine reading based entailment graph whenever it has an opinion about the answer to the question. But if either the premise in the text or the hypothesis, the question, are not in the graph, or both are not in the graph, we should use a large language model to find a P prime and an H prime that actually are in the graph, and or an H prime that are actually in the graph. And then if either the premise or the P prime that we found, or the H prime that we found, and the H or the H are in the graph, then we can answer the question. So this minimizes the non-directional influence of the language model. And I'm assuming, as I say, that it's really based on similarity. This is not a very good slide. I grabbed it from the paper. We have a paper in submission, and I think it's on archive, in fact. What this slide says is that if the text said, the question is, did Arsenal play Manchester United? Just a yes/no question for simplicity. The text says Arsenal obliterated Manchester United, etc., etc. And obliterate is not in our graph. So what we do is first we use the language model to embed the predicate that is missing from the entailment graph, namely obliterate, to find the most similar one. In fact, we do this offline using contextualized embeddings. So for the predicates that are in the graph, we actually find nearest neighbors to obliterate using the language model. And in the last step, the entailment graph itself completes the directional inference. And if that doesn't do it for us, then we give up. But actually, the entailment graph doesn't contain defeat. That is a nearest neighbor of obliterate. And in the entailment graph, among other things, defeat entails play. So we have an answer to our question because we found a P prime that was in the graph as entailing RH question. So we say, in fact, we can say more than just saying yes. We can give an explanation. We can say the reason that we're answering yes is that we think that Arsenal defeated Manchester United on the basis of this question of the entailment graph. So there's a little bit of explanation going on here as well. So here's some details about what I just described. I think that this just sort of says everything that I said before, except that it raises the question that there is no guarantee that the language model K nearest neighbor P prime, that was defeat. There's no guarantee that obliterate actually entails defeat. It's just the language model that thinks that they are very similar in their associative properties in the text. So we're taking a gamble here, because if obliterate does not entail defeat when we're talking about sports teams, then our assumption of transitivity of entailment is unsound. So is this going to work? Well, it turns out that it worked. It partly works. So this graph, the dull gray dotted line, is the entailment graph. The entailment graph on its own, with none of this enhancement. I can't do this. None of the enhancement by the language model. The green line, the green line is the smoothing effect, the effect of smoothing the premise. In other words, the effect of believing that if defeat is a close neighbor of obliterate, then it's entailed by obliterate. And that actually works right across the domain. You can see here a sort of reification of the weakness of the entailment graph on its own, that at the high precision end, it's pretty good, but it loses recall. So by the time it gets to 50% recall, it's at 50% precision. That is what we're trying to smooth away. However, the magenta line shows that language model smoothing is actually deleterious for smoothing the hypothesis, the question, right across the whole range. So why is language model smoothing asymmetrical for the premise in the text, but you shouldn't do it with the question? The answer is that there's, and this comes to my point of sort of using the language model for what it's actually learning. There is an oddity about the distribution of the words that the language model is building a similarity sphere, a similarity model on the basis of, which is that there is an increase in specificity. There's a sort of inverse relation between specificity and frequency. So the more just to simplify, the more frequent a word is, the more general it is, the more frequent a word is, the more specialized it is, and the more general the word is, the lower its frequency. I've got that, I keep getting that the wrong way around. The specific terms are low frequency, and the general terms, the more general terms are high frequency. So the words like dachshund are lower frequency than words like dog. Now, there's a sort of refinement to this point, which is that once you get to natural kinds like dog, then words start getting less frequent the more general they are. So there are fewer occurrences of vertebrate than there are of dog. But for the purposes that we're thinking about, the dominant influence is that if you look at the k nearest neighbors of a word in the language model, you will get more frequent words, because they will be the words that the language model has a lot of evidence for. So you will tend to get generalizations. And this is a very general technique with language models of all kinds. You see it in translation, that translations tend to be blander and more general than the text that you started out with. This is a well-known bias. And what it means is that when the language model finds nearest neighbors of the things that are in the graph, then it very often ends up with more general words than the missing P, the thing that is in the text that you're asking yourself whether it entails an answer to the question. Now, since specifics are often hyponyms, so dachshund is a hyponym of dog, and related generics are hyponyms like mammal, it's likely that P entails P prime if you take it as the nearest neighbor in the language model. So what this says is that you smooth the premise, the thing that is in the text, you're likely to get a generalization of the thing that is in the text, the relation, the word that is in the text. And if you get a generalization, it very often entails the thing that you started off. So big dog does entail being, being a dachshund does entail being a dog. So if you find out that being a dog entails whatever you're interested in the question, I'm skipping from entities to relations in a very free-handed way, then the answer to your question is likely to be reliable. However, by the same reasoning, the nearest neighbors of the question, the hypothesis, that are most likely to be in the entailment graph and are going to be the highest probability as neighbors, they are going to be hyponyms of the hypothesis. They're not going to be hyponyms. So they're not going to be things that are entailing of the hypothesis. They're likely to be things that are entailed by the hypothesis, but that's not what you want. That's going to be unsound. So the remainder of the talk I'm going to skip over because we've sort of tested the hypothesis that this is what is going on by using some certified hyponyms and certified hyponyms to smooth the premise and, most interestingly, the hypothesis. And what we find in this experiment, which you'll have to look on archive to find the details of, are that if you smooth the hypothesis with hyponyms, in other words, you don't just use the language model and get the most frequent things, which are likely hyponyms. You actually use things that WordNet tells you really are hyponyms of the hypothesis. Then you get an effect of smoothing on the hypothesis. It's a rather odd effect. It's a very slight effect if you just smooth the hypothesis on its own. But if you're also smoothing the premise, then smoothing the hypothesis actually is a very strong win across the board. And that is the black line that is showing on both of these graphs for premise smoothing and hypothesis smoothing. I'm going to wind up because I'm out of time. The conclusion of this is that you can smooth entailment graphs with language models on the premise or antecedent side, the text side. Whether you can also smooth the hypothesis on the consequent side, for instance, by using WordNet, is an open question. We've shown that if you do that, on a certain entailment data set, you get the effect. But it's an entailment data set that we constructed to be adversarial using WordNet. So we actually don't know whether this is going to work in the field. And actually, I'll tell you that I doubt whether it will, because WordNet is constructed essentially by hand and is also sparse. So I suspect that in the field, using WordNet to smooth won't work. So what we're actually looking at is as an alternative, because we're going to do that, but we don't think it's going to work, is to bias the language model in its generation of k-nearest neighbors towards hyponyms. We're going to try and teach it that it should be going down the generalization hierarchy rather than up. Whereas for the premise, we're going to teach it that it should go up rather than down. So we're actually looking at the language model on its own to see whether it is capable of doing this task if we train it the right way. I personally, being a romantic of the old school, am very skeptical about that. I think we're still going to have to use the entailment graph for its precision, but we will tell you about that at a later date. Thank you.
Thank you, Mark. This is a great presentation, great work. Regarding the recall issue, do you think if we combine between the entailment graph and have embeddings for the predicates of the nodes, while still keeping the relationship between the predicates for the precision, but we are adding to the presentation of the predicates, which is the embedding from the language model, do you think this could help on the recall issue?
Yeah, well, I think it helps on the generalization. It helps you. That's what we're actually doing. I didn't spell it out, but when we find nearest neighbors to the word, so we're something in the text that is missing from the graph, obliterate. We look at we have looked at all the nodes in the entailment graph, and we use contextualized embeddings. I mentioned it in passing, but it probably wasn't clear. We use contextualized embeddings in making the estimate of the k-nearest neighbors in the language model. So I think that we're already doing what you're saying to strengthen the extraction from the language model. I believe that's what you're suggesting, and it's a very good suggestion, and that's actually what we're doing.
Thank you.
Thank you very much, Mark. You mentioned the evaluation being a major problem in the beginning. Then you talked about open domain question answering. I'm not sure if this is the proposed solution for evaluation, or what are the options, how we can deal with this?
It's certainly not a solution yet. So open domain question answering evaluation is as other people have remarked, an open problem. There are no good open domain question answering data sets. The problem with question answering in general is that most questions have been asked and answered before. And if you're a language model, you've seen most of them before. And this is essentially, this is why even back in the days of Muck and its contemporary Trek, we did very well with bag of words question answering, because most questions that people ask are actually asymmetrical. So the question of who shot Kennedy is actually asymmetrical because nobody's interested in who Kennedy shot. I don't even know if he did. So if you answer these questions on the basis of bag of words, you do very well. It's only when you do the error analysis that you see that there is a special category of questions that you're failing on completely. And in fact, in the days of Muck and Trek, we did bag of words. And when we did the error analysis, we found that, of course, sports is the domain where you fail. So one of the questions in the test set was, who did George Frazier beat? But another question was, who beat George Frazier? And bag of words gave exactly the same answers. So it's really only when you do the error analysis that you see what's going on in standard question answering tests. So we are having to devise our own question answering tests. And we have done that in a paper that we published last year, I think, on generalizing the graph that I talked about from binary relations to unary relations. And we generated an adversarial question answering data set from that we think is along the right lines. So it's a data set that essentially consists of directional questions. And we generate that from one set of news text, identifying frequent relations that people are interested in over entities that people are interested in. And we use those to generate questions which we answer from a completely different set of text using the entailment graph and whatever methods come to hand. So I regard what your question as being an important open research question to actually find a way of evaluating open domain question answering.
So the suggested answer seems to be to build hard evaluation sets.
Yes.
That cannot be resolved by bag of words approaches in general.
Yes, because
this can apply to different tasks, not only question
yes,
answering.
I think so. So question answering is one of those tasks where high precision matters, because one false positive means that your user loses faith completely. So in the same competition, we were asked, what do frogs eat? And the answer came back, herons. And if you get that as a user, you never use your app ever again because you know that it's faking it.
So one question that I have is, do you have issues with antonyms? Because you have been talking about synonyms, hyponyms, but we know that antonyms are very bad for distributional models because they happen in exact same places where synonyms happen. So is it something that is causing you trouble?
No. The easy answer is no, because this thing is based on actual evidence from the text. So there is evidence in the text that if you look at the if you look at the, for instance, in the sports domain, beating a team is an antonym in a funny sense of winning against a team. And we will find evidence that if you win against a team, you play against a team, and if you beat a team, you play against the team, but we will not find evidence that if you play a team, you beat the team. So we will not find an entailment relation between the antonyms. Having said that, the reason that this domain is so difficult
is that, of course, Watford plays Arsenal on many occasions, and sometimes they win and sometimes they lose. So unless you do event recognition as well as part of your entailment mining, you will conclude that winning entails losing. And in that, you have a different problem from antonyms than the one that the language models have. For language models, the synonym, the antonyms are very similar in association, so there's no directionality between them. Our problem is that multiple events of the same type may lead you to make erroneous inferences of entailment unless you're very careful. And of course, we do pay attention to dates when we're deciding whether beating someone entails winning. But without qualification, antonyms as a whole are not a problem. In fact, on that experiment that I didn't really have time to spell out with using WordNet, we actually constructed a special antonym data set to make sure, to compare ourselves with the language model. So that was actually an adversarial data set of that kind. So we're fine on the whole with antonyms, provided we do event reference.
So there has been work that has been proposing to use language models as knowledge bases themselves, right?
Yeah.
So here you're interested in using language models just for the entailment mechanism, but you're not really interested in the prior knowledge that they have. And kind of you had just like touched a little bit on that aspect. So the question is, how do you make sure that you're using the language model just for the entailment capability and you don't really get interference from what it knows about the world from the text it has been trained on?
So it is, I mean, I'm sort of maybe getting confused. So the entailment graph embodies common sense knowledge. In fact, one of the reasons that probing text for this class of entailments probably isn't going to work is that these are the things that are obvious to every speaker of the language. I'm thinking I'm missing your question, but I can't hear you.
Okay, so Kat, you have in the text that one team won against another one, but actually kind of from the previous knowledge of the language model is actually the other way around. And I'm wondering to what extent you can get an interference.
Oh, I see.
There.
Oh, okay. There is a simple answer to your question. We segregate the role of the language model. If the entailment graph answers the question, then we rely on the entailment graph for its precision. If the language model has a suggestion, we only look at the language model in this very restricted role of, does it think that there's something in the entailment graph that is likely to be entailed by the thing that's in the text? So there is the danger of the language model is that the language model will come up with a hyponym and will think that, and that is in the entailment graph, and but it is not the thing that the language model comes up with is nailed by the thing that is in the text. And that is an error that will show up in our error analysis. But it's rare because of this distributional bias in the language model itself. So we're really chaining this thing down. And it's what I referred to in my first slide. We're only using the language model for what it actually learned from the text, not for what we think it might know from the text. And we hope that that's sound.
Wonderful. We're unfortunately going to have to leave it there. I know there are other questions, so let's thank Mark again for a wonderful talk. So we're running a little bit behind schedule because we started a little bit late. We'll have a break, caffeinated beverages, other things out in the courtyard, and we'll kick back off at 11 o'clock. At 11, so about 20 minutes.
Leave this